So in the last lecture, we looked at some theoretical optimization results. In this lecture, we're going to turn around and look at some practical situations. All right, so we have here a situation where a farmer has 2,000 feet of fencing, and he wants to know what are the dimensions of the biggest rectangular field he can enclose. And by biggest, we mean has the largest area. All right, so I'm kind of thinking my way through here. What are we going to do? Well, just at a very high level, right, this is a question about rectangles. Right, so okay, let's draw a rectangle. Right, get a picture here for us to work with. And if I have a rectangle, I know it's got these two dimensions. Let's call them the length L and the width W. All right, now let's go back to the question. What is the question talking about? Right, well, it says I have 2,000 feet of fencing. So I'm thinking at some point I'm probably going to want to talk about the perimeter of this thing, because that's how that's 2,000 feet is going to be the around the rectangle distance. So let's get that formula up here. The perimeter of a rectangle is twice the length plus twice the width. And the question is, what are the dimensions? Okay, that's good. I've got length and width in my diagram, in my formula here. And I want the biggest rectangle, right? So I'm looking to maximize the area. Okay, well, good. Now what? First, I want you to keep your focus over here on this equation, right? That is the one that we are trying to optimize or maximize. Right now, we're in kind of the same situation we talked about before, where we've got too many variables. I don't know how to work with an equation that has two variables like L and W. I need to pare this down. All right, so this perimeter equation, this is going to be my constraint equation. Right? I know that the perimeter is 2,000 feet. I'm assuming I'm going to use all 2,000. Right? Why would I hold back? If I hold back some of it, then it's going to make for a smaller enclosure. So I'm going to put 2,000 in here for P. And now I'm going to simplify this a little bit. Right? I notice that all the coefficients are even. Right? So let's divide everybody by 2, and I'm going to rearrange. I'm going to put the variables over on the left where they belong. So this becomes L plus W equals 1,000. Now, I want you to think about the situation we have here. Right? The sum of the two numbers is constant, and I want to maximize the product. Well, this is the situation we saw in the last lecture, in the theoretical lectures, and we saw that when we have this situation where the sum is constant and you want to maximize the product, that maximum value occurs when the length is equal to the width, and they are both equal to that constant divided by 2. All right, so the optimal dimensions, the dimensions that give me the biggest area, will be a 500-foot square. All right, so again, remember when we're doing word problems, we always want to answer the question at the end. So I would say the length and width should both be 500 feet. Right, and there's my answer. Now, if you didn't watch that lecture, if you didn't watch that lecture, it kind of looked like I just pulled that formula out of a hat, right? So on the next slide, I'm going to actually walk through the process, and it's going to be the same process we used to derive this formula in the first place, so you can see how that would work. If you feel you're squared away on that, you're welcome to jump ahead to the slide after that, where we'll be doing another problem that doesn't exactly fit the model, and we have to use that kind of more direct approach. All right, so I've got the same scenario. Let me sketch it in here again, right? I've got length and width, and my perimeter is 2L plus 2W, and it's the area that I'm looking to maximize. Well, I'm going to kind of proceed the same way. I'm going to put 2,000 in here for the perimeter, and then divide everybody by 2 purely because I can, and it makes the numbers smaller. Right now, again, I'm in the same predicament. I need to get that area formula down to one variable. So I'm going to do that by taking this constraint equation and solving this for L. L is 1000 minus W. Now I'm going to substitute that into here. Then my area formula becomes area equals 1000 minus W times W. And if I multiply that out, this is 1000 W minus W squared, and that's a quadratic equation that we're trying to optimize. We're trying to maximize. We know how to do that. We have a formula, right? The maximum value of a quadratic equation whose graph opens down, which this one does, right? Because the leading coefficient over here is negative. I've got a formula for that. Right, the formula is W equals negative B divided by 2A. Now don't get mixed up here, just because the terms are rearranged. Let me rearrange this here so that it's in kind of the usual order. This is negative W squared plus 1000 W, right? So B is 1000 and A is negative 1. And let's see, the negatives cancel. 1000 divided by 2, look at that, is, sure enough, 500, right? The exact same number we got before. And then we need to get the length, right? To get the length, take this value for W, put it into this equation. The length is 1000 minus 500, which is 500. And yes, awesome. We do end up with the same result this way. All right, so now I've got another situation here. We have this thing, it's called a Norman window, right? It looks like a rectangle. It's easier if you draw the semicircle first. It looks like a rectangle with more or less a semicircle on top, right? And I want the dimensions that emit the most light. So again, I'm trying to maximize the area. Right, I want the area to be as big as possible, and I know that the perimeter has to be 20 feet. I've got only that much border material, for example. All right, so how am I going to do this? Well, I'm going to let this be the height, and I really don't want to go beyond 2 variables here. So, but look, say I let this be R. It's an obvious thing. We're talking about circles, right? We always want to know the radius. In any area, all these formulas we use are going to involve the radius. And if this is R, then what is the base of the rectangle here? Well, if this side is R, then this side is also R, which means the base here is 2R. Awesome. That gives me what I need to know. The area of this thing is 2RH, that's the area of the rectangular piece, plus half the area of a circle, right? Because we only have half of it up there on top. So it's going to be 1/2 pi r squared. Right? Well, that's good. Right? Now I need my constraint. Right? I need something that that's going to use this 20 feet here. So what is the distance around this thing? Well, it's we'll call it perimeter. Perimeter is just the distance around. So I'm going to kind of start down here and work my way around. Right? The base there is 2r. Then we've got the right-hand side, that's h. Plus, now I need the distance around the circular bit. Well, the circumference of a circle is 2 pi r, but I only have half a circle, so it's a half that. And then finally, I have this other vertical side here, so that's another h. Okay, awesome. So let's see. We know the perimeter has to be 20, so I'm going to put 20 in there for p. 20 equals 2r plus, let's see, I could add these two h's together, plus 2h plus these twos, the twos are going to cancel there, so that's plus pi r. Okay, now I have to, unfortunately, I can't reduce the numbers any because there's, I've got the 20s and the 2s, and that's nice, but there's no number in front of that pi r term. So I can't divide by 2 without bringing a fraction in here, which I probably don't want to do. So now we have this big question here. I have to solve for one of these variables. Which one should it be? Well, theoretically, I mean, you can go with either one. You'll get the right answer either way. But when I'm doing these things, I'm always looking at this and saying, what's the easiest way, right? How can I minimize my work going forward? If I try to solve for r, I'm going to get 2r plus pi r equals something. Then I'm going to have to factor out an r and divide both sides by 2 plus pi. Okay, I'd rather not get 2 plus pi in my denominator. So let's try solving for h instead. Right? If I move the 2r and the pi r over, this becomes 2h equals 20 minus 2r minus pi r. Then I have to divide both sides by 2. And I'm going to go ahead and do it this way. I'm going to say h equals 20 divided by 2 is 10. 2r divided by 2 is, it's going to be minus r, minus pi over 2r. I'm going to, I don't know, maybe this will be easier, maybe it won't, they're just leaving the 2 in the bottom. But, uh-oh, I'm looking ahead. Oh, no, you know what? I'm going to take that back. You see, it helps to look ahead. Let's go ahead and leave it 20 minus 2r minus pi r over 2. And here's why. Right? I'm looking ahead. I'm seeing my next step is going to be to substitute this into here. And there's only one h in here, and there's a 2 out in front. That 2 that's out in front is going to cancel the 2 in my denominator, and the fractions are all going to go away. All right, so let's do that substitution. Area equals 2r times 20 minus 2r minus pi r over 2 plus still 1/2 pi r squared. All right, you see now those those 2's are going to cancel, right? That's nice. Now let's distribute the r into there. 20r minus 2r squared minus pi r squared plus 1/2 pi r squared. And let's see, I can combine these two terms here, the pi r squared parts. This becomes 20r minus 2r squared minus 1/2 pi r squared. Okay, now I'm going to rearrange. I'm going to bring the r squared terms out in front. So this will be minus 2r squared minus 1/2 pi r squared plus 20r. And I really need this to look like a quadratic equation, so I can use our vertex formula, yeah? So to do that, I need to have just r squared times the number. So I mean, we can factor that r squared out. What's left is negative 2 minus 1/2 pi plus 20r. And that's what I need. Right now I can go to my formula for the coordinate of the vertex. Right? And if I do that, I get I don't want to write under that h, sorry, I'm running out of room, so I'm going to clean up here just a little bit. I'm going to get rid of the diagram, which we're not really going to need anymore. So I can jump up here. Get my pen back. I can jump up here. Right, the vertex is going to occur at r equals negative b, that's negative 20, over 2a, that's negative 2 minus 1/2 pi. Okay, this is actually going to clean up not too bad. This is negative 20 over, let's distribute that 2 into there, negative 4 minus pi. And now I can factor a negative out of the bottom, right? Make this minus 4 plus pi, and the minuses are going to cancel. And this turns into 20 over 4 plus pi. And there you go, right? That's my r value. It's not a particularly pretty R value, right? But sometimes they aren't. Now, at this point, what do? Because my next step is to find the value of H. And to do that, I have to take this somewhat unpleasant expression and substitute it into here. And I'm going to get a fraction over a fraction, and I'm going to have to do some kind of off-the-wall common denominators, and you absolutely are free to do that. If this was me, what I always tell my students, right, the one of two places where it's okay to go to a decimal is when you're doing a practical problem, right? Because if you're working at a factory, right, you absolutely do not want to go to the shop foreman and tell him that the radius that's going to maximize the size of his window is 20 over 4 plus pi. That is not going to be a happy conversation for you, okay? So we're going to need to go to decimals, right? And if you do that, I got my calculator over here. I'm going to do 4 plus pi. And I'm going to divide 20 by that, and we get, oh, we don't get that. Sorry, let me do this again. 20 divided by 7.1415926. That's more like it. Oh, it comes out really 2.8004957. So I'm going to say this is 2.8. Then you can come back over here, put 2.8 in here. This is 20 minus 2 times 2.8 minus pi times 2.8 over 2. 2.80177. Okay, came out really close, right? As a matter of fact, if I was going to that shop foreman, I would say the optimal size let's say is 2.8 feet tall. And now you see here's what I say, that really is a coincidence. The numbers are not exactly 2.8 for each one. If I want to tell him the width, remember, it turns out we do need the diagram. Remember, our diagram looked like this, and this was 2r down here. So I would say 2.8 feet tall and 5.6 feet wide. All right, so this is the end of our discussion of optimization. In the next couple of lectures, we're going to continue our discussion of quadratic polynomials by looking for ways to model quadratic polynomials. In other words, if we're given information about points on the curve, right? For example, if we're given 3 points, how can we find the equation of the parabola, the quadratic equation, that passes through those points?